Hello. Ram, can you hear me?
Yes, sir, you are audible.
So let us start today.
Sir, your voice is
Last
very low.
very low. Now is it okay?
No, sir.
Oh. Okay. Hello. Can you hear now?
It's a bit better, sir.
Maybe there are some problems with the network.
No, sir, your voice is clear, but the volume is a bit low.
Volume, but I have given the full volume. Okay,
Now
I'll.
it's okay. Now
Now it's
it's okay.
better, sir. Now it's better.
Oh, nice. Okay, okay. Uh, um, okay, can you see the white screen?
Yes, sir.
Okay. So last day we had discussed about the solving the recurrences. Okay, mainly the iterative method and master method. So what is master method? Let us recall once, and after that we will go for proving the theorem. So master theorem says that a greater equals to 1 and b greater than 1 be two constants, okay, be two constants, then if Tn can be written as at n by b plus f of n, then if Fn can be bounded as big O of n to the power log a base b minus epsilon, then Tn can be written as or bounded as n to the power log a base b. Okay. Uh, then for the second case, this was case 1. Case 2, uh, if Fn equals to theta of n to the power log a base b, then Tn can be bounded as theta of n to the power log a base b log of n. And number 3, the case 3 was that if Fn can be bounded as omega of n to the power log a base b plus epsilon, and if a into f of n by b is less equals to some constant less than 1 c into f of n, then Tn can be bounded as theta of f of n. So this was the master theorem. Okay. So this is known as master theorem. By the way, here n by b means either floor value of n by b or ceiling value of n by b. Okay. So now we will go for proving the theorem, but really we will go for considering the one simplified form. Simplified form means here you see if n by b is not exactly or the n is not an exact power of b, then we have to consider either the floor value of b or the ceiling value of b. So for the simplicity, First, we will prove the theorem when n is an exact power of b. So that means n by b is an integer value. Okay. So we don't have to go for finding whether n by b we have to consider floor value or ceiling value. So first we will prove the theorem when n is an exact powers of b. After that I will give some idea that how we can go for the proving the generalized value of n. So that means n can be any value, any integer. Okay. So let us go for proving the theorem when n is an exact powers of b. Right. So this is what I need. So for the proving the theorem, we will prove three lemma. Okay, three lemmas we will prove. The lemma one says that let a greater equals to 1 and b greater than 1 be two constants, same as the previous, be two constants, and if Tn is written as a Tn by b plus f of n, okay, then Tn can be bounded as two terms, that is one will be a terms of big O, another will be a terms of theta. Okay, later I will prove that what are these two terms. So the lemma one says that if this is given, right, here I should write n is an exact power of b. Okay, n is an exact power of b. So then Tn can be bounded as two terms like this. So here it may not be big O of this, and later I will find that what should be the actual term. So I will write this later, because if I write this, then it will be difficult to prove. That means something like that. So first let us go for iterating the term. After that we will go that how we can bound this Tn, and also we can write the lemma at that time. Okay, not now. So let it is given that T is equals to a T n by b plus f of n. Since n is an exact powers of b, therefore we are not writing floor value or ceiling value here. Okay, we are considering the integer value. Good. So then let us iterate to the next term. That means a, this value T n by b will be iterated as a T n by b square plus f of, you see, when it was n, it is fn. So this value will be f of n by b plus f of n. Okay. If you find some difficulty, immediately you ask the questions, or you can raise your hand, okay, so that I can go on repeating the same thing. But please try to understand that what we are doing, right? So if Tn is equals to this, in the next iteration what we will get? We will get that a this. So we can write a square plus, sorry, a square T of n by b square plus a into f of n by b plus f of n. Okay. In the next iteration, what we will get? We should get a cube T of n by b cube plus a square f of n by b square plus a into f of n by b plus f of n. Okay. So if we go on iterating this term, this can also be done by using the recursion tree. Okay. So here uh, this is iterated up to third. Then if we go on iterating up to ith term, what we will get? A to the power I t of n by b to the power I plus, you see, a to the power I minus 1 f of n by b to the power I minus 1 plus up to a square f of n by b square plus a into f of n by b plus f of n. So we can write the ith iteration as this. Okay. So here you see, this is a series. From here we can think this as a series. So we can write this equals to a to the power I t of n by b to the power I plus sum of a to the power, say anything, k b f of n by b to the power k. K varies from 0 to I minus 1. Okay. So now see, Tn can be expressed as a to the power I t of n by b to the power I plus sum of a to the power k f of n by b to the power k in this way, and k varies from 0 to I minus 1. Okay. Now when this will iterate, that will be written in the lemma, or here in this case we can consider that when each subarray or when each sub problem contains single element, then we can say that our recursion will terminate. So what is the meaning of this? That means if Tn equals to theta of 1 when n equals to 1. So the terminating condition is that when the number of element is equals to 1 in any subarray, it will be terminated. Okay. So let us consider that the ith iteration is the terminating condition. So if the ith iteration is the terminating condition, then what we can say? Let us erase all these first. The terminating condition is the ith iteration. So we can write from here t of n by b to the power I must be equals to 1, so that this is equals to constant theta of 1. Okay. So the number of terms, number of input in the subarray n by b to the power I must be equals to 1. That implies I equals to log of n, or if we consider all are base 2, then we can write Lg of n. So the value of I is equals to log n base 2, right? Now, if we put this value here, what we will get? If we put this value, then we can get that Tn is equals to, see what we will get, Tn, this value is equals to a to the power I, here a to the power I, that means a to the power, sorry, here it will be base b. Okay. I am very sorry. So it will not be 2, it will be log n base b. This is b to the power I, not base 2. So Tn is equals to a to the power I is equals to log n base b plus t of 1, we have considered n by b to the power I equals to 1 plus sum of k equals to 0 to I minus 1, that means log n base b minus 1 a to the power k f of n by b to the power k. Okay. So that equals to, we can write n to the power log a base b theta of 1 plus the sum. Just we are writing for the, since I have used I, then you can also write j, because in the book you will find that this is written as j. I am writing here k equals to 0 to log n base b minus 1 a to the power k f of n by e to the power k. That we can write theta of n to the power log a base b plus this sum. The same thing, k equals to 0 to log n base b minus 1 a to the power k f of n by e to the power k. Okay, so we have proved, or we have shown that Tn can be written as a bound of theta into the power log a base b plus a sum of series. Okay, so let us erase all these and let us write properly that what is Tn. So Tn from lemma 1 we can write that Tn can be expressed as theta of n to the power log a base b plus sum of a to the power k f of n by b to the power k. K varies from 0 to log n base b minus 1. So lemma 1 says that if a greater equals to 1 and b greater than 1, and Tn can be expressed as Atn by b plus f of n, where n is an exact power of b, then Tn can be written as this. This is the lemma 1 that we have to, or we have already proved. Okay. So what we have got, Tn has been expressed one bound and another series. So if we can find the bounds for this sum, then we can find the bounds for Tn. Okay. So now our task is to find the upper bound, lower bound, and the tight bound for this term, nothing else. Okay. So let us go for the next. So that is known as lemma 2. So please check the statement of the lemma 2. I am just proving the lemma 2. Okay. Lemma 2 is simple as the master theorem, where it says that if a greater equals to 1 and b greater than 1 be two constant, then a greater equals to 1 and b greater than 1 be two constant, and fn is a non-negative function. Okay, non-negative function. Already we have told all these during our master theorem. Fn is a non-negative function. Then a function gn, we are defining the function gn as the term that we have got from the lemma 1, a to the power k f of n by b to the power k, where k varies from 0 to log n base b minus 1. Okay, gn can be bounded as, so lemma 2 is finding the bounds for G. It says that if Fn is equals to B go of n to the power log A base B minus epsilon, then for obviously epsilon greater than 0, Gn is equals to B go of n to the power log A base B. So this is the statement of lemma 2, that if this is equals, these are all given, and Gn is equals to this, then Gn can be bounded as, if Fn equals to this, Gn equals to this. Case 2, you can find some similarity between the master theorem and this, but not the same. Okay, so don't get confused. If Fn equals to theta of n to the power log A base B, then Gn can be bounded as theta of n to the power log A base B log n. Case 3, if Fn equals to omega of n to the power log a base b plus epsilon, and if a into f of n by b is less equals to c into f of n, then gn is equals to theta of f of n. Okay, so here we are finding, obviously the c is less than here. Okay, c is less than 1. You have to keep this in your mind, and whatever we are doing, all are for sufficiently large value of n. This should not also be forgotten, that all the things that we are doing is for large value of n. So lemma 2, the statement is that Gn can be bounded as these three conditions. If these three conditions are fulfilled, then we can find the bounds for G of n. So let us prove all these cases. So let us start with the first one. Okay. So the first is given that if case 1, if Fn equals to what big O of just a minute. So if Fn is equals to given as big O of n to the power log a base b minus epsilon, then we have to find the bounds for g of n, that we have to find. Okay. So now f of n is given as this, and gn is equals to sum of a to the power k f of n by b to the power k. So here we can find the value of f of n by b to the power k, because fn is given as this. So let us write again, fn equals to big O of n to the power log a base b minus epsilon. Therefore that implies f of n by b to the power k is equals to order of n by b to the power k to the power log a base b minus epsilon. Okay. Now if we take the value of gn, then we can write this is equals to sum of a to the power k big O of n by b to the power k to the power log a base b minus epsilon. Okay, this is gn. We know this is given, so we have just substituted the value of n by b to the power k. Okay, right. So here please write the k is equals to log n base b minus 1. So gn is equals to this. So let us write it again from this one. So what we have got, gn is equals to sum of a to the power k order of n by b to the power k to the power log n base b minus epsilon. K is equals to 0 to log n base b minus 1. So we can write this equals to n is not dependent on k, so we can take this n value outside of the summation. So we can write n to the power log a base b minus epsilon from the sum. We can extract this, and this equals to, we can write the whole term as the big O, whole term as the big O. So big O of a to the power k big O of 1 by b to the power k to the power, okay, 1 by b to the power k to the power log n base b minus epsilon, that we can write. That is equals to, we can take this big O as the outside of whole, because if this is the upper term, okay, upper bound, then the whole should be the upper bound. So we can take big O as the out of the, or big O as the total term. So n to the power log a base b minus epsilon, and this is equals to, this is equals to a to the power, here listen it very carefully, a to the power k. Now b to the power k to the power this, okay, we can write b to the power, actually it is minus 1. So if we take this, what we will get, b to the power epsilon to the power k, and here we can write b to the power log n base b, okay, uh, sorry, this is a, so this is a log a base b to the power k. Okay, please check it thoroughly. If I do any mistake, let me rectify that, sir, you are doing something wrong. So this value was given f of, I wrote wrongly here, that log n, it should be log a base b. Here I did the mistake that I have replaced n, but it should be log a base b. That is equals to big O of n to the power log a base b minus epsilon, that is fine. Then a to the power k, b to the power epsilon to the power k by a to the power k. Why? Because b to the power log a base b, from the property of logarithm, we can write b to the power log a base b equals to a to the power log b base b, and which is equals to a. Okay, so that to the power k is equals to a to the power k. So we can write big O of n to the power log a base b minus epsilon. These two terms will be raised. Oh, sorry, here all these are k equals to 0 to log n base b minus 1. Here also there will be some k equals to 0 to log n base b minus 1. Here also b to the power epsilon to the power k, k varies from 0 to log n base b minus 1. Okay, so we are getting that Gn is equals to big O of n to the power log a base b minus epsilon into sum of this. Okay, so next we can write, let us start from here again, big O of n to the power log a base b minus epsilon into sum of b to the power epsilon to the power k, where k varies from 0 to log n base b minus 1. So you know this is the GP series. Okay, so b to the power 0 to the power b to the power epsilon to the power 0, then b to the power epsilon to the power 1, GP series. So we can write this sum as n to the power log a base b by n to the power epsilon, we can write into b to the power epsilon and up to this term, so r to the power n minus 1. So here r is b to the power epsilon and number of terms here log n base b. Okay, we got r, the common ratio is b to the power epsilon, and number of terms are log n base b, because we are counting from 0 to log n base b minus 1. So this much of terms are there. Therefore, r to the power n, r to the power, sorry, r is b. Therefore, we can write that r to the power means b to the power epsilon to the power log n base b, right? Minus 1, r to the power n minus 1 by r minus 1. So here r is b to the power epsilon 1. So what we will get? We can write this value as b go of n to the power log a base b. See, b is a given value n by b. Already we have said a equals to this and b greater than or are two constants. So b to the power epsilon minus 1 is also constant. So this constant term can be absorbed by this big O, because constant, if we multiply with the value of constant c, it will also be a constant. So therefore we can omit this constant term. Okay. So here you see we can write this term as like this: b to the power epsilon to the power, we can just I am writing in another term, b to the power log n base b to the power epsilon minus 1. We can write this by b to the power epsilon minus 1. Okay. So here we can write n to the power b base b, this term by the same property of logarithm. So just we are replacing this term as n to the power log b base b, same as this, by the property of logarithm. Now this is equals to 1, so we will get this is equals to n to the power epsilon. So in the next term, what we can write? We can write this equals to n to the power log a base b by, sorry, n to the power minus epsilon is equals to n to the power epsilon minus 1 by b to the power epsilon minus 1. In the next term, we will iterate all these. Okay, iterate means discard all these values. So let us check. That will be equals to so what we can write, this equals to 1 by b to the power epsilon. We can consider this equals to, or we can erase all these values. We may not consider this value at all, because constant term will be absorbed within this big O. So we can write big O of n to the power log a base b into n to the power epsilon minus 1 by n to the power epsilon. You can write this also, no problem. If you have any confusion, you can write also this, that b to the power epsilon minus 1. Now you see what will happen. N is a positive value. Okay, so you may wonder that how it is going on. So we can write this as per the definition of the big O of n. We can write, for the simplicity, let us write, otherwise you may get some trouble. Some constant into n to the power log a base b into n to the power epsilon minus 1 by n to the power epsilon into 1 by b to the power epsilon minus 1. That's why I was telling, because this is the definition of big O, that it will be less than this. Now consider this n to the power, n is a positive value. Already we have considered epsilon is a positive value. So n to the power epsilon minus 1 by n to the power epsilon will always be less than 1. Always. this term always will be less than 1. And since b is positive, epsilon is positive, this is a constant, we can consider this is another constant and which is greater than 1, because we can choose b value a large and epsilon a large value. Therefore, b to the power epsilon minus 1, b to the power epsilon minus 1 is greater than 1, and hence this value is also less than 1. Okay, this term is also less than 1. Now, if we replace this less than 1 value by 1 and this less than 1 value by 1 also, then what we will get? The previous term is less than n to the power log a base b into 1 into 1, and that is equals to c into n to the power log a base b, which is the definition of big O of n to the power log a base b. Okay. So here you see, we have proved the case 1 that Gn can be bounded as big O of n to the power log a base b. Okay. So if you have any confusion, please you ask. Otherwise, in the next case again you may find some difficulty. Anyone, do you have any query? Can you hear me?
Yes, sir.
Yes, sir.
Do you have any query? Have you understood what we have discussed?
Yes, sir.
Okay. So from case 1 we have got that Gn can be bounded as big O of n to the power log a base b. Okay. I do not know whether I will get time for the next. Do you have any class now? Karam, do you have any class now?
Sir, we have theory of computation class.
From
Not now exactly, but from I guess 3:45, I guess.
3:45. So can I take another 15 minutes? Then this theorem will be completed.
Okay, sir.
Okay. Okay. So let us go for case 2. So in case 2, it is given that if Fn is equals to theta of n to the power log a base b, then we have to show that Gn is equals to theta of n to the power log a base b log of n. So as for the previous one, we can write Gn is equals to sum of a to the power k f of n by b to the power k. Don't forget to write this log n base b minus 1. So that is equals to sum of a to the power k into theta of n by b to the power k to the power log of a base b, because fn is theta of n to the power this, therefore f of n by b to the power k will be equals to this. That is equals to sum of a to the power k into theta of uh, theta of n to the power log a base b by b to the power log a base b to the power k, as for the same as previous that we have discussed. Okay. Right. So we can take out this n term from the outside of this sum. Therefore, we can say this is equals to n to the power log a base b n to the power log a base b theta of sum of a to the power k into, you see again, b to the power log a base b is equals to a to the power log b base b. So a, and hence it is 1 by a to the power k, right? As b to the power log a base b is equals to a to the power log b base b, and which is equals to a. Therefore, this value will be a to the power k. So this is equals to n to the power log a base b theta of sum of 1, and this k varies from 0 to log n base b minus 1. How many terms are there? Log n base b. And if we take this sum, it will be equals to n to the power log a base b theta of log n base b. Because if we take the sum of 1 up to this term, it will be equals to this. So that is equals to, we can write n to the power log a base b into theta of log n base 2 log 2 base b. This is constant, b is constant, 2 is constant, therefore this can be absorbed by this theta as per the definition of theta. So we can write this as equals to log n, n to the power log a base b theta of log n base 2. So that is equals to theta of n to the power log a base b log of n. Now see, case 2 is also proved. Okay, case 2 also proved. Now let us go for case 3. Case 3, it is given that f of n is equals to omega of n to the power log a base b plus epsilon. You are not going to this. Now what is given? Gn is equals to sum of a to the power k f of n by b to the power k. So k is equals to 0 to log n base b minus 1. You see, for k equals to 0, we will get the minimum value of g of n, and that is equals to f of n. And for k equals to 1, it will be a positive term. K equals to 2, that is gn will be increasing. What is the lower bound for g of n? For k equals to 0, and that is equals to a to the power 0 f of n by b to the power 0, so which is f of n. So we can write the lower bound for g of n is fn. We are giving this value as 1. Okay, so the lower bound for gn equals to this, and here another condition is given as f of n by b to the power k is less equals to c into f of n. Okay, so sorry, this is later I will write. This is given. This condition is true. This condition is given. Now what we can do? We can iterate this term up to k. Okay, so we can say that a to the power, that is gn, what is given? Gn is given as equals to sum of a to the power k f of n by b to the power k. This is given. So we can write k equals to 0 to log n base b minus 1. So we can replace this value with Suppose from here what we can conclude, if we iterate this term, up to k, so that means can we write that this value will be less than a into k f of n by b to the power k must be less equals to c to the power k f of n. Can we write this? Please note, a is a positive constant, b is also positive constant, c is less than 1. So we cannot simply say that yes, always it will be right. But think about that. A is greater or equals to 1, b is also greater than 1, c is less than 1. So if we increment this, if we go to the power of a to the power k, can we say that yes, this will be correct? Yes. Why? Think about when n tends to infinity, that is very, very large, as you can think. Okay, also beyond that. So Fn, when n is tends to infinity, f of n is much higher than f of n by b to the power k. So whatever the value of a you choose and whatever the value of c you choose, always it will be much more larger than f of n by k. So though it may be less than 1, if you multiply this, it will be greater than k to the power k f of n by b to the power k, because n is too large. So we can write this. Now this can be replaced as sum of k equals to 0 to log n base b minus 1 c to the power k f of n. Okay, and this is equals to, we can write fn is not dependent on this, therefore we can say that it is c to the power k. K value is this. Now think about k is equals to 0 to log n base b minus this. We can do that, we are increasing this value up to infinity. So since all are positive, k is positive, though it is less than 1, but this is positive, so if we add more terms, this one will be greater than this. Okay, so what we can say, what is the sum of this value? K equals to 0 to infinity c to the power k is equals to f of n 1 by 1 minus c. This is the sum of this series, and c is less than 1. Okay, so 1 by 1 minus c must be greater than 1. So we can write this value is equals to some constant into f of n. Okay, where we can write c is greater than equals to 1 by 1 minus. So we can write this is equals to big O of f of n. So let us consider this is 2. Now from equation number 1 and equation number 2, what we can conclude? You see, Gn equals to omega of f of n, Gn equals to big O of f of n. So can we write that Gn equals to theta of f of n from equation 1 and equation 2? So therefore this is case 3. This also proved. So we have proved all the 3 cases of lemma 2. Okay. Now lemma 3 is proving the master theorem for n is an exact powers of b. So from lemma 1 what we have got, Tn is equals to theta of n to the power log a base b plus g of n, where gn equals to the sum of something like that, a k f of n by b to the power k, k equals to 0 to log n base b minus epsilon. that we have already proved. Now from lemma 2, case 1, theta into the power log a base b plus this is b go off into the power log a base b. From case 1 already we have proved this, and we can write this is equals to theta of into the power log a base b. Why? Because theta is already containing b go, so it is not required to write it again. It will be absorbed by theta. So theta of this plus b go of this must be equivalent to theta, because theta is containing already this one, so we don't have to write anything extra. Case 2, from case 2 we can get the value theta of n to the power log a base b plus theta of n to the power log a base b log n. Since this is higher than this term, therefore this will be equals to n to the power log a base b log of n. Case 3, theta of n to the power log a base b plus theta of f of n. Since fn is larger than this, therefore we can write this is f of n. So now check. The master theorem was that Tn can be bounded as theta of n to the power log a base b for case 1, theta is theta of n to the power log a base b log n for case 2, and theta of f of n for case 3. So we have proved the master theorem for n is an exact power of b. Okay. So now how to prove for all values of n? Just we have to consider n is equals to floor value of n by b or ceiling value of n by b. Okay, and you have to go on iterating the term in the same way. So home task is prove the master theorem for any value of n. Okay, right? So this is all about the proof of the master theorem. Please check the book, read it, and if you find any difficulty, let me know. Okay. Do you have any query? Any question?
No, sir.
Do you have any question?
No, sir.
Hello.
No, sir. No, sir.
Okay. So then I must stop the meeting. How to stop? First, recording.